Hello, and welcome to my humble abode. Very strange for you to be here, and not our usual meeting place, but okay, all jokes aside, it's not April Fool's or anything. It's just things are getting really serious out there, and it's getting harder and harder to gain access to campus with a blackboard. So I guess we're going to be meeting like this for the rest of the semester. So I have bought something that I can write with, and I'm going to try to use OneNote and all that kind of good stuff, try to make this lecture as normal as possible. I'm not happy about it, but hey, what are you going to do? Math must go on. And yeah, I shall be recording lectures from home now. I'm not happy about it, but we'll do the best we can. So let's actually just jump into it because we only have 50 minutes. I don't have time to tell you about yesterday, which is when I realized that I couldn't really go where I wanted to anymore. I am going to share screen with you. Boom, and there we go. Okay, so it's Math 1207, as you are well aware, Calculus 2, and we're going to start with a Q&A, which was the only question I got from based on my last lecture. So let's start there. Hi, Jhevon. Last lecture, we went over the Maclaurin series for sine and cosine functions. Would the Maclaurin series for a tangent function be the same as the Maclaurin series of sine over cosine, or would it be different? Now, I'm going to start the lecture with something that would actually answer this, but let me just say right now, I guess, and you can hear it repeated later, yes. And the answer is yes because of something that we covered in the last lecture where we spoke about the convergence of Taylor series and what it means for a Taylor series to converge to the function that generated it. And we also know that the Taylor series for the sine function and the cosine function and the exponential function and the function 1 over 1 minus x converge to their generating functions on the interval of convergence. Now, what that means, and this is something that I'm going to drive home a little bit later as well, is that in that situation, the series is the function. It's just another way of writing the function. It's kind of like me saying, well, is 1 plus 1 and 2 the same thing? Well, kind of, yeah, but they look different, but they're the same. It's just another way of writing down the same thing. So when I say the Maclaurin series for the sine function, you can think of it as the sine function. It is the sine function. However, whatever way in which the sine function will behave, the Maclaurin series for the sine function is going to behave. And so because we know the tangent function is given by the sine function divided by the cosine function, it does stand to reason that the Maclaurin series of the tangent function will be the Maclaurin series of the sine function divided by the Maclaurin series of the cosine function. Did I say cosine last time? I feel like I said cotangent. So the short answer to this question is yes. Now, I wouldn't necessarily recommend that way of computing the Maclaurin series for the tangent function, even though it is very doable, and I will show you some sources that computes it that way. I would probably rather use multiplication to do it. So that is, think of, just write down a generic series for the tangent. Just think of it as, you know, the sum of an x to the n. Right? So it's a0 plus a1x plus a2x squared plus a3 blah, 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 dot, dot, dot. And I would think of that as the tangent. Multiply that by the cosine. Expand, multiply out group-like terms, and then that would give you the tangent x times cosine of x, which from the trig identity is equal to the sine of x. So you can set that thing that you multiplied out equal to sine of x, and then you kind of equate coefficients, and you can actually figure out what the a's have to be in order to generate the series. You can do it that way. You could also do it by directly using the formula for Taylor series. So let me try to write here. Okay. So ways that you can do this is just think of tangent x times cosine x, set that equal to sine x. So this would mean that if you don't know what the series for this guy is, so you just write down a generic Maclaurin series, dot, dot, dot. We do know the Maclaurin series for the cosine though. That's 1 This is very awkward. I mean, I've been writing on this for a day, but it's still 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot, dot, dot equals, and we know what the Maclaurin series for sine is by now. So this is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus dot, dot, dot. So basically, you would multiply these guys out here. So that changed the color. So you would just take A0, multiply that, multiply that, multiply that. Then you take A1 and multiply that. So you just multiply out all of these guys, you'd group like terms, and then you'd set the coefficients equal to each other on both sides. And that will allow you to solve for the A's using a system of equations. And you'll solve for the first few. You'll solve for them one at a time. And yeah, that's one way that I would do it. Another way that I would probably recommend is just use the formula. Just set tangent x equal to f of x, and then use the series n goes from 0 to infinity of the nth derivative evaluated at 0, if we're finding the Maclaurin series, x to the n, over n factorial. And just calculate a bunch of derivatives, plug in 0. So the thing is, to find the general formula, fn of 0 is difficult to find here. So you'd only find the first few terms and then just put a dot, dot, dot. It's very hard to actually find it. So those would probably be the way I would go about it. Now, yes, you can, you could also use the fact that tangent x is equal to sine x over cosine x. And you could just write that as x minus x cubed over 3 factorial plus dot, dot, dot. And then you can do over 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial plus dot, dot, dot. Well, it should be a minus or whatever. But basically now you just do a long division of polynomials. So you're going to have, you're going to take the sign, which is 0 plus x minus plus 0x squared minus x cubed over 6 plus da, da, da. And then out here, you're going to have that 1. You're going to have that 1 minus x squared over 2 plus da, da, da. And then you go, like I told you guys how to divide by that. And you can get the first few terms starting to populate here. And what's going to show up here is going to be your tangent function. That being said, I would not ask you to do something like this. So while I appreciate the curiosity behind the question, it is not something that would be very relevant to our class. The reason being because of this reason over here that I mentioned. It's very hard to find a general formula for the nth derivative here. There are ways to do it, but you would actually need to know quite a bit of math beyond calculus 2 to be able to write that down. in shorthand. So what I would do, I collected some links here, which pretty much go through the methods that I show if you wanted to see it in greater detail, or if you wanted to try it and then check your answers. So this here is using the Taylor series expansion to find the Maclaurin for tangent x. That's this version here. You can use the trig identity and multiplication of series. That's what I used here. And you can use trig identity and division of series, which is what I spoke about here. And this is just if you wanted a shortcut version. This link here actually tells you a nice short formula for the nth derivative here, except it uses something called a Bernoulli number, which again, way beyond calculus 2 levels. So it's not a nice thing for me to ask on an exam, and I wouldn't do it. And I already feel bad about spending so much time talking about this question. But since no one asked me any other questions, I guess I could spend some time on this one. Yeah, so that's how I would go about finding the Maclaurin series for tangent. In short, yes, I can think of it as the Maclaurin for sine divided by the Maclaurin for cosine, because the series, once they converge to these functions, the function is the series. The series is the function. Whatever I can do with the series, I can do with the function. Whatever I can do with the function, I can do with the series, etc. And that kind of leads nicely into scrolling down here. So I'll provide these notes, by the way, which, even though I'm providing the notes, you really should write your own notes. You should be taking your own notes. Probably not in this Q&A section if you're not interested, but as I move on to the lecture, it is very important. It is one of those things where if you just sit down and you watch me write everything for you and do the problems for you, it's not going to be good for your learning and retention. You are going to want to take your own notes and try problems on your own whenever I ask you to do that. So, but if you're interested more about this, check out these links. It'll give you a lot of useful stuff, and this will be provided in a PDF, so you can click on them. But you can also take a screenshot and type in the links right now if you want. So yeah, moving on, that is what I kind of wanted to go into next. So getting into the lecture now, last time we spoke about convergence of Taylor series, which was very important. So we know how to compute a Taylor series. You find the nth derivative evaluated at a point, multiplied by x minus x naught to the n over n factorial. You sum, n goes from 0 to infinity. This generated a series associated with a function f of x. Now, we went over examples when this series actually did not converge. We also saw examples that it converged to something other than the function f that you started with. And we've seen examples where it does converge to the function that it started with, namely the guys that I asked you to memorize, the 1 over 1 minus x, the e to the x, the cosine of x, the sine x. The Maclaurin series that I gave you for those 4 functions, they actually converge to the functions that generated them. And that's an important thing to take away. And the important thing that you wanted to note from the last lecture is, where's my mouse here? That if your remainder term, which we defined last time, approaches 0 as n approaches infinity, then we know that the Taylor series, n goes from 0 to infinity of the nth derivative evaluated at some point x naught, x minus x naught to the n over n factorial, will actually approach the function that generated it. And when this happens, I'm still getting used to happen. My handwriting was bad already before, but now it's even worse. When this happens, what that means is that f of x is equal to its Taylor series, at least on the radius of convergence. Its Taylor series. And that is a very important thing to know. It's a very useful thing to know. And throughout this lecture, I'm going to go into some uses and applications of knowing that fact and how it can be helpful. And hopefully that gives you some insight into why this would be important. Now, I want to also show an example. Now, a point that was emphasized, I did emphasize this, but it bears repeating, bears re-emphasizing it, is that when a Taylor series converges to a function, anything that can be done to the function can be done with the series. Any formula that the function works in, the series will work in. Any identities that the formula is involved in, the series will work for that as well. And I wanted to do an example of deriving the derivative of sine x, which some of you might find this easier than when we derived sine x before in the in Calc 1, where we had to remember the addition formula for the sine function in order to do it. But here, I just want to show you that everything that we know about the function can be determined and rediscovered based on how the series behaves. So for example, if I wanted to find the derivative of the sine function, notice that this is me asking about the derivative of this particular series, which we have memorized by now. What is the Maclaurin series for the sine function, sine of x? So hopefully what you thought or said was this guy, 2n plus 1 over 2n plus 1 factorial. Now, if you didn't say that, very bad, naughty, naughty. You should be studying what's in the last lecture. Or the last two lectures. I forgot what lecture. It's been a crazy time. It's been a crazy time, really. So that is what we have. And we know because this converges absolutely, absolute convergence tells us that we can swap the series and the derivative. Now, notice that this is x to the 2n plus 1. And just so that we can see what's going to happen a little bit easier, I'm going to write the 2n factorial as 2n plus 1 times 2n factorial, which again, we explained last time why that is the case. And so what you can do here is you can just actually just differentiate. So we have the series of the minus 1 to the n over 2n plus 1 times 2n factorial. That's just a constant as far as x is concerned. To differentiate x to the 2n plus 1, of course, you bring the power down and subtract 1 from the power. Now what you're going to notice is that this guy cancels that guy. And so this becomes the series as n goes from 0 to infinity of minus 1 to the n, x to the 2n over 2n factorial, which, by the way, we know is the series for cosine. And so you can prove that the derivative of the sine function is the cosine function. And once you understand series, some people might actually find that a lot easier than how it was done in Calc 1. But this is just another example to show that pretty much anything you can do with a function, you can do with its Taylor series, provided the Taylor series converges to the function. And you can do calculus with it and a lot of mathematical operations with it as long as you're within the region where that series converges absolutely to the function. And it's one and the same. Everything will coincide. All the formulas will remain the same. You can think of the series as the function. So when you go back and you think about that question that was asked, can we think of the tangent as the division of the sine Maclaurin series divided by the cosine Maclaurin series? Yes, because sine divided by cosine, whether I think of them as the functions or as series, they will always give me the same result. They will behave the same way. And so that's important for you to know. That's something that's going to be important. And we're going to apply that moving forward. So yeah, so that's just something I want to reemphasize. Whenever the remainder term approaches 0, and I told you what the remainder term looks like, the Taylor series will approach the function, and then we can think of the function as being the Taylor series. And they are, from now on, interchangeable in the same way that 1 plus 1 is interchangeable with 2. Also last time, I left you guys with some examples to do. Here were the first 2 examples. So this is the next thing that we're going to go into. Now, hopefully you actually tried these. If you did not try this, pause the video and try this right now. highly recommended. You do not want to have me do everything for you. It is not going to be fun when the final comes around, if that's the case. So make sure you try it, and make sure you watch the video and you actually attempt it and ask me questions about anything that you have. I'm of course very happy to answer questions, and now I guess I have even a little bit of extra time to answer questions since I'm not driving into campus anymore, because no one will let me in. Hashtag stay at home. Okay, so, and this example, by the way, is a very important example, asterisk. Now, asterisk example 2. So it is definitely the kind of problem that I would ask on a test or the final. So you can expect this, a problem of this type, to actually show up. Very common problem type, very standard kind of problem to ask in Calc 2. Find the Maclaurin series of a certain function and use it to evaluate the integral of that function. And usually the function will be a nasty kind, the kind that you can't really find an indefinite integral for. And so you are going to use the series to approximate the integral. So it's a very common problem type. Now, hopefully you guys actually attempted this, and pull this stuff out. This thing is very sensitive. I don't know what happened. Okay, so something else popped up on my screen here because it clicked by accident. Hopefully you're still seeing. Hopefully you're still seeing the OneNote document. Because whenever my mouse and this thing kind of interact, the computer tries to click both at the same time. Yeah, I have to be very careful. Anyway, let's actually jump into it. Hopefully you actually tried it. So let's see what example 1 would look like. Let's actually run through this bad boy. Where are we? Okay, so let's move down to example 1. So 1. So how did you find the Maclaurin series for sine of 2x? Pause the video and tell me what you would do. Okay, so hopefully this is the way you approach it. Now, one thing that you could attempt doing is finding all the derivatives, plugging in x equals 0, and computing the coefficients one at a time, hoping to find a pattern. Not the best way to do this, especially the fact because that is a sine function there. And the thing is, we know about the sine function. So we know that the sine of x is equal to the series n goes from 0 to infinity of minus 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. This means because the sine function is the series, anything I do with the sine, I can do with the series. Meaning, if I plug in 2x squared into the sine function, it is the same as me plugging in 2x squared into the series. And so that's actually the answer to part A, find the Maclaurin series. That is it. So once you have those series memorized that I asked, yeah, drawing boxes for some reason is really difficult here. It's going to take some practice. That's your answer. Once you have those 4 Maclaurin series memorized, you'll get a lot of traction out of them. So hopefully you have those memorized by the time a test comes around. Because the person who has this memorized, this is a problem that it takes them 2 seconds to recognize and 20 seconds to write down the answer to, whereas someone else will spend a good 10 minutes deriving each constant and then trying to come up with a formula and then plugging it in and moving on. So you'd save a lot of time by memorizing the thing that I asked you to memorize. Now, Because I know the Maclaurin series for the sine, I can look at this integral in a whole new way. Now, the first thing you should appreciate is that the indefinite integral of sine of 2x squared, we don't know what that is. Does not have an elementary antiderivative. So we can't actually do that by hand, believe it or not. So what we would do here is instead replace that guy with the series that we just derived. Now I see something here. This 2 should be an n. I don't know why I put a 2 here. Minus 1 to the n, and 2x squared 2n plus 1 over 2n plus 1 factorial dx. Now, because we have absolute convergence, I can switch the series and the integral. And I still don't know why the pen does that sometimes. Okay. So it's going to take some getting used to. Oh, gosh. Okay. Set it to 1 over 10. F minus 1 to the n. Let me write this out in a slightly different way. This is 2 to the 2n plus 1. And then it would be x to the 4n plus 2 all over 2n plus 1 factorial dx. And so what I'm going to do now is I'm going to do this integral first. And it turns out, because it's a power series, the integration is very trivial because it's going to be the power rule, right? So this whole part here, the minus 1 to the n, 2 to the 2n plus 1 over 2n factorial, that's just a constant. So that guy pretty much stays put. And then I'm going to integrate the x part because I'm integrating with respect to x. So this would be the minus 1 to the n, 2 to the 2n plus 1, x to the 4n plus 3, because you add 1 to the power, divided by, well, you're going to divide by the new power, 4n plus 3. And we had a 2n plus 1 factorial here before. And then I'm going to plug in 0 and 1/10 by the fundamental theorem of calculus. So now, if I plug in 1, I would have minus 1 to the n, 2 to the 2n plus 1, x. I'm plugging in 1. Okay, so I'm plugging in 1 for 1/10 for x. So this is going to be over 2n plus 1 factorial, 4n plus 3, times 10 to the 4n plus 3. This is going from n goes from 0 to infinity. Now, the problem said to, using your answer above, estimate this integral using a sum of 2 fractions. You do not need to simplify your answer. So I would just evaluate this for 2 terms. Now, if you plug in n equals 0, you would have 2 over 3 times 10 cubed. Plug in n equals 1, you would have minus 2 cubed over 3 factorial, and plug in 1 here, that would be times 7. Plug in 1, that will be times 10 to the 7. Now I'm going to write one more term here, just for giggles. Plug in n equals 2, I would have 2 to the 5th over 5 factorial times n equals 2, that's 11 times 10 to the 11. And this is your answer right here. Like, that was about to be the best box I drew all day, but it was not meant to be. That's your answer. That's approximating the integral as a sum of two fractions, which is probably nice if I actually write an approximation sign here. So that is approximately equal to this. Now we move on to part C. Given upper bound for the error in your estimate above, what do you think? Now, some of you obviously now can tell why I wrote the third term, because, and you can't just say it, you have to actually give a reason. Like normally I'll write the question, justify, blah, blah, blah. So the justification is by, that's right, the alternating series approximation theorem. The error of the first two terms is bounded above by the magnitude of the third term. This is 2 to the 5th over 5 factorial times 11 times 10 to the 11. By the way, just for fun, let's actually compute what that is. So let me look that up here. So it's 2 to the 5th divided by 5 factorial, that's 120, times 11 times 10 to the 11. And that, ladies and gentlemen, is how big you think the error is. 2.4. 2.4242. And that actually repeats forever. Yeah, which seems big, but oh, it's not big. It's times 10 to the minus 13. So this is actually a pretty good approximation, actually. So that's like 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 2, 4, 2. So the error is that it's for this particular function, adding two fractions was actually a surprisingly good approximation. And that's because you're very close to 0. The sine function behaves a lot like a polynomial there. We know because sine x over x approaches 1 as x approaches 0. It means when you're getting close to 0, your sine x behaves like the function y equals x. And so it's already kind of has a polynomial behavior. So you expect to get really close really fast if you're very close to 0. And you're between 0 and 1/10. You're on the interval 0 to 1 over 10. Pretty close to 0. So that's actually a good approximation. And that is how you do a problem like this. So find the Maclaurin for sine, use it to estimate this integral. Why is your estimate good? So it comes down to you having formulas memorized that you can take advantage of, plugging the series into the integral to evaluate the integral, approximating it with however many terms that you were asked to do it. And when you notice that you have an alternating series, which you can notice from here, you can use some of the series approximation theorem, which I'm pretty much always going to test you on the alternating series approximation theorem, by the way. So anyone who gets part C wrong is, yeah. Okay, so by the alternating series approximation theorem, we know that the sum of the first n terms is approximated by the magnitude of the n plus first term, which means the error is always going to be less than or equal to the magnitude of the next term. So if we add the first two terms, how close are we to the actual answer? The magnitude of the third term tells us. And yeah, that's the problem. So what I would like you guys to do now is to pause the video. Very important that you actually try this. Please, please do it. Pause the video and repeat the example for the function e to the minus x squared and the integral 0 to 1 of e to the minus x squared. So we're going to repeat, go through this exact same thing again. And I'll leave this here, pause the video. Okay, now hopefully you did that. Let's just go through example 2. So in problem 2, so now our function is e to the minus x squared, right? That is our function. Now we know, or we should know by now, that e to the x is the Maclaurin series for that is n goes from 0 to infinity of x to the n over n factorial, which means e to the minus x squared is going to be the series, well, you plug in minus x squared. And this means that your e to the minus x squared can be thought of as the series minus 1 to the n, x to the 2n over n factorial. Now this is for later. Okay, and all right, let's try to draw a box again. Ooh, come on, come on, come on, come on, come on, come on, come on. I don't know why it goes so far, okay. And that, ladies and gentlemen, is the best box I've drawn all day. That's the answer to part A. Part B, we want to approximate the integral 0 to 1 of e to the minus x squared dx as a sum of two fractions. I am just going to realize that this is exactly the same as integrating this series. And then by absolute convergence, that is the same as the series of the integral. I can compute that. Then that is just the series, and the integral is, so this is integral from 0 to 1. Yeah, I'm not sick, don't panic. That was just like a sneeze out of nowhere. Not like self-quarantine or anything. I really had the intention of going into campus, but it just didn't work out for me. Well, that's what happened yesterday, and I just decided not to bother trying again today. The whole ordeal just lost all my motivation to even try anymore. Okay, so now we'd integrate this. Again, the minus 1 to the n over n factorial is a constant. So I'm going to integrate the x part, add 1 to the power, divide by the new power. And fundamental theorem of calculus, that's between 1 and 0. So this is going to be the series and goes from 0 to infinity of minus 1 to the n over n factorial times 2n plus 1. Now we were asked to approximate this with the sum of two terms. So plug in n equals 0, you would get 1, minus plug in n equals 1, you would get 1 over 3, compute a third term. Now, because I saw that the next part is asking me about how good the approximation is, and I know the alternating series approximation theorem is what's going to be, because that's what Jhevon's going to ask me about, I'm going to automatically compute a third term, even though I know it's not going to be a part of my answer. So this is when n equals 2, that will be 1 over 2 times 5, or 1 over 10. Now this is the answer to part B. Part C, you justify by the alternating series approximation theorem. The error is bounded above by the magnitude of the next term, which is 110. So this one has an error of about 0.1. Now, if I actually check what that is, just for the fun of it, integral of 0 to 1, and I'm using Wolfram alpha here, as you can probably guess. Right, so the answer is 0.75. If you round it to 2 decimal places. Wolfram gave me 6. And what you would notice is our approximation is actually 2/3, which is 0.67. So yeah, we are less than 0.1 away there. Magic of the alternating series approximation theorem. Very nice theorem, very nice problem. And like I said, a problem like this you can expect on the next test, whatever that would look like, and on the final. Very standard problem for a Calculus 2 class. So here, again, me memorizing the Maclaurin series for the exponential function allows me to find the Maclaurin series for this variant of the exponential function. And then I can, if in an integral, I can replace the exponential with that series, because e to the minus x squared has no elementary antiderivative. You couldn't do this by hand even if you wanted to. But we can do it by series. This is the series answer. And by using 2 terms, I'll be 0.1 away from the answer. Now, you will notice that Wolfram alpha, for example, gave me to 6 decimal places, which basically means Wolfram alpha just kept adding fractions until it realized the next fraction would be less than 0.000001, right? And then it's like, okay, I can stop adding these fractions now and output that as the answer. And if I wanted, oh, Wolfram, I want more decimal places, then it would just keep adding more fractions until the next fraction was less than the amount of decimal place accuracy that you wanted. And that's how it's done. So if you say, I want 5 decimal place accuracy, it'll just keep going until the next fraction is less than 10 to the minus 5. And yeah, that's how it would get you the answer to a certain number of decimal places. So this is how your TI-89, Wolfram alpha, a lot of computer algebra systems will actually calculate integrals this way, because with series, it's trivially easy. It boils down to going from something that's impossible to compute by hand to something that you can use the power rule for integration on. When does that happen? It happens because of series, very applicable. So this is one of the reasons why series is very important. And like I said, they are important beyond calculus class. But one of the reasons we love them in calculus is because they make the actual performance of calculus a lot easier, like integration, differentiation. Well, it's very rare that you'll need it for differentiation, let's be honest. But integration, as you guys are well aware from the first part of this class, can be quite difficult. Yeah, series provides another way to do this. Let's move on. So The next example that I left you guys with was this guy. Now, hopefully you actually tried this, but the rest of this lecture, what I have planned, I'm kind of going to rush through it. So take it of your own accord to actually pause before attempting something. There is something that I'll actually have you pause for on purpose because it's actually beneficial. It would be something that I would ask you on a test. But a lot of the rest of these things that I'm going to mention, it's a little bit for fun or curiosity's sake, but it's beneficial in the sense that if you continue to go down this path of like, you know, the hard sciences, you're going into physics or engineering or anything like that, where you're going to use a lot of math, or if you're going to be a math major, eventually you'll get to a point where a lot of these things I'm about to talk about, people are going to expect you to know about them, even though a lot of your classes wouldn't even talk about them to begin with. But it'll be kind of things that you'll be expected to know. And so I think I'll actually talk about them. And some of them are pretty cool, like this example here. Prove Euler's equation. So there's an equation, e to the I theta is equal to cosine theta plus I sine theta. And I guess when I talk about polar coordinates, I'll go a little bit deeper into the intuition behind this. But at the moment, it might not seem very intuitive, especially if you're not aware, if you've never taken a complex a class with complex numbers. But this is a very, very useful equation. And it gives rise to something that's called by many the most beautiful equation in all of mathematics. And that's what this link here is about. So it might be of interest later, but we are going to get to it. So the hint is series might come in handy. So you can pause this and try to prove this equation using series and see if you get the answer. So here's how we'd go about doing this. So a couple things. So last time, okay, there we are. Last time I told you that I was the square root of -1. This is just a definition. It's the imaginary unit, it's called, and it is one of the basic elements of a complex number. This means, of course, though, that if you were to square I, you would get -1. It also means that if you were to cube I, it's the same as I squared times I, that's just minus I. And then it also means that if you were to raise I to the fourth, that's just I cubed times I, which is minus I squared, which is -1 times -1, so you get a +1. And then you'd realize that I to the fifth would give you I, and then the pattern repeats. Right? Now, that's the first thing that you'd want to know here, or hopefully you'd actually recognize that if you tried to prove this. And so what we can get is, if I look at e to the I theta, notice that this is just a series of I theta to the nth power over n factorial, because that's from the Maclaurin series for the exponential. Now, what I can do is, and I'll actually write out some terms here so you can actually see how things are going to be simplified here. Plug in n equals 0, you'd get 1. Plug in n equals 1, you would get I theta over 1 factorial. Plug in n equals 2, you get I squared theta squared over 2 factorial. Plug in n equals 3, you get I cubed theta cubed over 3 factorial. Plug in n equals 4, you get I to the fourth theta to the fourth over 4 factorial. I'll just do a couple more so you'll see a pattern eventually. Over 5 factorial plus I to the 6th theta to the 6th over 6 factorial plus ... Now, based on the above, this is just going to be I theta, can't really do anything there. But the I squared I know is -1. So this is actually minus theta squared over 2 factorial. I cubed we know is minus I. So this is minus I times theta cubed over 3 factorial. I to the fourth is actually +1. So this is plus theta to the fourth over 4 factorial. Then I to the 5th is just I theta to the 5th over 5 factorial. Now, I to the 6th is going to be minus 1, so it's minus theta to the 6 over 6 factorial plus dot, 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 etc. And here's something that you can do. We can group these guys. We can group all the guys that don't have i's in them, the guys that have i's in them. The i's have it. So who doesn't have an I? Well, 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6 over 6 factorial plus dot, dot, dot. Who has the i's? Well, theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus, the next one would have been theta to the 7th over 7 factorial plus dot, dot, dot. And hopefully you actually recognize what those guys are. The first one is actually cosine of theta. That's the Maclaurin series for the cosine function, plus I times that you'll notice is the Maclaurin series for the sine function evaluated at theta, which is pretty cool. So you have that the exponential can be dissected or cut up into components where a part of it behaves like a cosine and a part of it behaves like a sine. And you end up with this really cool and super useful equation here. I'm getting better at drawing boxes, believe it or not, even though, spoke too soon. Spoke too soon. Okay, and this equation is called Euler's equation. Now, there is something that's very nice here. Let's move this guy down a little bit. Talk about you later. And you can notice something cool here. If we set theta equals pi, why would you do that? Well, just look at what would happen. This gives you that e to the I pi is equal to cosine of pi plus the I times sine of pi. Now, cosine of pi, we all know is -1. Sine of pi, we all know is 0. So essentially, this means that your e to the I pi is equal to -1. That is going to be a fact that's going to be useful in a lot of classes beyond this, particularly differential equations and complex analysis, be the math classes where you'd use it, and those are used everywhere in applications. But this also means that e to the I pi plus 1 equals 0. This equation is very important. Mostly for aesthetic reasons, actually. This is called Euler's equation, Euler's identity. Now, it's a very surprising result, but it's also a very beautiful result, and a result that people geek out about all the time, because it's very strange that all these guys combined in this way to make this equation. It's a very short equation, and one thing that a lot of math people geek out about is the fact that, one, to fully appreciate this, you're going to have to come to this from the perspective of a class maybe like abstract algebra, which really talks about dissecting everything in terms of patterns and symmetry and all that good stuff. So this equation has tons of meaning in that perspective. So because if you were to think about the real number system, or even number systems in general, there are certain important things and certain important elements in that number system. Things like the additive identity, multiplicative identity, and the operations that you can do with the set of numbers. So like addition, subtraction, multiplication, division, setting things equal to each other, raising things to powers. So we have a bunch of operations that we know about, addition and subtraction. which you can think of that as just addition, really. Subtraction is just kind of addition in a different direction. You can think of multiplication and division, which you think of that as multiplication, really. Division is just kind of like multiplying by a reciprocal. You can think of exponentiation, which again, that's connected to logarithms as well as radicals. And you can think of E, which, as I mentioned, you guys weren't in there in Calc 1. E to the x, most important function in all of mathematics. It's very useful in Calc 1, very useful in calculus for deriving a lot of things. And pi is obviously an important constant. That shows up all over in geometry. And I is the main way that we were able to define the complex numbers, which allows us now to find n solutions up to multiplicity to any polynomial equation. And that was important in its own right. Now you have an equation where all of these important things come together. You have the exponentiation operation. You have the multiplication operation because you have the I times pi. You have the addition operation because there's the plus sign. You have the equal operation. You have the additive identity of the real numbers and the complex numbers, which is the number 0. You have the multiplicative identity of the real numbers and the complex numbers, which is the number 1. You have the important and ubiquitous constants E and pi, and you have the guy that invented the complex numbers that allows us to solve polynomial equations beyond our wildest dreams and do all sorts of things with surprising ease in the world of complex analysis, the imaginary unit I. All of them combined in this one equation to come together in such a beautiful format. And a lot of people really like that. It's considered by many, if you were to Google, what is the most beautiful equation in all of mathematics? This is going to be the guy that's going to be number 1 on a lot of people's lists. And if you actually go to this link, you can see a guy who's way more exciting than I am, way more excited than I am right now, because I've been recording and I'm already getting digital eye strain from this stuff. But you can watch that video and have someone else talk about it. Po Shen Lol, Professor at Carnegie Mellon, has a nice video where he talks about that stuff, and I linked it there for your interest. So that's another application of Taylor series, because I can use it to, you can use this to prove this nice equation, which, yes, this is kind of an aesthetic use of it, but it's actually a very useful equation to know in differential equations, complex analysis, all sorts of things where you'll need an exponential, as well as it's just used all over the place. You won't believe it. If you become a math major, you'll realize how important that equation is. And engineers and physicists will also appreciate how important this equation is as well. Yeah, so that's one application. That's really cool. Another application is the binomial theorem. Which is probably, I had some more things planned for today, but we'll probably push those into tomorrow's lecture or another lecture. I'll probably record Friday's lecture tomorrow where I'll actually finish this up. Is the binomial theorem. Now this is something that's pretty cool. Hold on, so I want to spend like 5 more minutes here. Now I'm wondering, do I want to spend my 5 minutes here or here? Now let's just do the binomial theorem. Okay, so binomial theorem. This is a guy that tells us how to expand binomials. Now a binomial is just a sum of 2 terms. So something like x plus y, that's a binomial. Now you look at something like x plus y to the n, and you just want to know how would you expand that. It turns out you can write that formula down as a series, namely this series. And the binomial theorem is the theorem that tells us that. So for example, let's say I wanted to expand, where is my pointer? Okay, so let's say I wanted to expand, for example, x plus y cubed. According to this series formula, this is going to be 3 choose 0, x to the 3, y to the 0, plus 3 choose 1, x to the 2, y to the 1, plus 3 choose 2, x to the 1, y to the 2, plus 3 choose 3, x to the 0, y to the 3. Now, I mentioned some term here that you probably never heard of before. This is called n choose k. It's a very important number. The first place most people actually see this number is in like probability and statistics. It enables us to count something very important. It is the number of ways to choose k objects from n objects. In no particular order. We have a formula for that, and it is n factorial divided by k factorial times n minus k factorial in the denominator. Okay, another way to actually think about that formula, which is the one that's going to be most useful for the application I'm going to bring up, is it's n times n minus 1 times n minus 2 dot dot dot. You'd multiply it down to n minus k plus 1. Now after this point, you'd have n minus k factorial, which is going to cancel the n minus k factorial in the denominator. So you have all of this I don't know, over k factorial. Okay, and when I taught the class, what's 1108 last semester, I actually derived why the formula is this way, but you don't have to know. Okay, so that's the formula. So example, if I look at 10 choose 3, this is going to be 10 times 9 times 8 over 3 factorial. 3 times 2 times 1. So you have 3 factors on top. So the bottom is just 3 factorial. And on top, you just have 10, subtract 1, and count down as many factors as there are in the factorial that's in the denominator. So in our general formula here, you'll notice that the numerator has k terms in it. So that's how you do. The number of, the factorial tells you the number of factors you need in the top. Let's simplify this. 3 can go into 9 3 times, 2 goes into 8 4 times. So this is 120. Now, what is the significance of that number? Like I said, it's the number of ways to choose k objects from n objects in no particular order. So for example, if I had 10 people standing over there and I wanted to choose at random a group of 3 people from those 10 people, just pick 3 random people, put them in a separate group over here. And there's no order. The order in which I pick them is not going to matter. So whether I pick John and Paul and then Mark, it doesn't matter. That's the same group as if I picked Paul, then Mark, then John. It's considered the same. The order does not matter. How many ways could I choose 3 people out of a group of 10 people? 120 ways. That's 10 choose 3. That's why it's called the choose. It's the technical term for it. It's called a combination. So this is called a combination, as opposed to something called a permutation, which you'd also hear about in probability class. So that's an important number, and it also tells us how to expand things according to the binomial theorem. So if I go back over here, applying that formula to these guys over here, 3 choose 0 is actually 1. So that's x cubed. 3 choose 1 is 3. 3 choose 2 is also 3, as it turns out. 3 choose 3 is 1. And so that's how you'd expand it. X cubed plus 3x squared y plus 3xy squared plus y cubed. That's how you'd expand. So this actually gives you a formula for how to expand things. And I could do the same thing with, say, x plus y to the fourth and expand that as well using this formula. Another way to look at this, which you might have noticed or you might have seen before, is something called Pascal's triangle. So this starts with a triangular pattern of 1, and then you have ones, and then to get the new line, you start with a 1, you add the two lines above, the two numbers above it, so that's 1 plus 1 is 2, and you end with a 1. So we keep going. 1 plus 2 is 3, 2 plus 1 is 3, end with a 1. Then you'd go 1, 3 plus 1 is 4, 3 plus 3 is 6, 3 plus 1 is 4, then you end with a 1. One thing you'll notice here is that the lines in the Pascal's triangle actually tell you about the coefficients in the binomial theorem. So for example, if you look at this line right here, you'll notice that that gives you the 1, 3, 3, 1. It actually tells you the coefficients in the binomial theorem. So these binomials actually coincide with Pascal's triangle. And so this line down here, the 1, 4, 6, 4, 1, that actually tells me what it would look like to expand a binomial to the fourth power. So using this, it will be x plus y to the fourth. It's going to look like 4 choose 0, x to the fourth, plus 4 choose 1, x cubed, y. Notice that I start with the highest power on the x and then count it down, and then I start with the lowest power on the y, which is 0, and count up. While following this pattern, 4 choose 2, this would be x squared, y squared, plus 4 choose 3, this would be x, y cubed, plus 4 choose 4, y to the fourth. So you have a group of 4 people. How many ways can you choose no one? One way, just choose no one, right? That should be an equal sign. 4 choose 1 is going to be 4. 4 choose 2 is going to be 6. 4 choose 3 is going to be 4. And 4 choose 4 is 1. So that's how you expand to fourth power. So that's something that a lot of people expect you to know how to do. They'll expect you to know the binomial theorem. If you've had a college education, heck, if you had algebra in high school, that's something that they kind of expect you to know. I would tend to expect my calculus students to know that, even though I wouldn't like it, but I would actually bet that most of them don't know it. But whatever, I digress. That is, this should be a fourth power here. That is the binomial theorem, and you'll notice the coefficients 1, 4, 6, 4, 1 is in that thing. Okay, what does it all mean, Baz? Why are you telling me all this? Okay, so here's something really cool. We can generalize this, and we can generalize this in a special way. And I'm going to show you something cool after we generalize it. If I use the Taylor series, try to find a Taylor series for x plus y to the n, and I find it in just the way you think. I can think of y as a constant here, think of this as a function of x, find derivatives, plug in x equals 0, blah, blah, blah. It turns out I can show that this would give an, I don't know what's going on. This would give an infinite series, k goes from 0 to infinity, of n choose k, x to the n minus k, y to the k. It'll be an infinite series, and we generalize n choose k to be that formula, n times n minus 1, multiplying all down k factors, n minus k plus 1, over k factorial to work even if n is not a positive integer, which usually that's how it's defined. It does make sense from the probability standpoint for n to be anything other than a positive integer, because you're choosing something from a bunch of things. If we say n can be anything, it doesn't have to be a positive integer, and I use this formula for n choose k, some really interesting things can happen. So, for example, so Taylor series we can use to derive that. Where are we? So, for example, let's look at this bad boy right here. Let's say I wanted to expand x plus 1 plus x to the nth power. According to this formula, that would be the sum from k goes from 0 to infinity of n choose k, well, x to the k, if I use that formula, right? So I just plug in 1 in place of x and plug in x in place of y in the formula that I wrote down in the Taylor series version. So, by the way, this would mean that something like 1 plus x to, let's write a non-integer power, a half, okay? So I'm thinking of the square root of 1 plus x. What would that look like if I were to expand it? What does it mean to expand a half power? Or so that's what we're going to look at here. Basically, this is going to just be the series of a half choose k, x to the k. In other words, that is going to be a half choose 0, x to the 0, plus a half choose 1, x to the 1, plus a half choose 2, x squared, plus a half choose 3, x cubed, plus dot, dot, dot. That's what it would look like for me to expand this. Now, what does it mean to take a half choose 0? Well, if I look at the top definition, n choose 0 is always going to be 1, x to the 0 is 1, so the first term is 1. A half choose 1, n choose 1 is always going to be n by the formula, so that is just going to be actually a half x. A half choose 2, what's that going to look like? How do you choose two things from a half a thing? Again, in physical reality, it doesn't really make much sense, but if I generalize this formula, it turns out to actually be correct by just looking at it as the Taylor series. And so a half choose 2, what it looks like is the denominator is going to be 2 factorial. The numerator is going to just be 2 factors where I start at a half and then I subtract 1. Plus, for a half choose 3, 3 factorials at the bottom. Then on the top, there are going to be 3 factors, 1 for each of the factorials. So it starts at a half, subtract 1 again, and so on, x cubed, plus dot, dot, dot. This is going to be 1 plus x over 2. Now here, this would be minus x squared over 8, that looks like, because it's 2 times 2 times 2 in the denominator. Here, the 3's are going to cancel. And you would have something like 5x cubed over 2 times 2 times 2 times 2 over 16, it looks like, minus dot, dot, dot. And that's the expansion. So for example, what this would mean, for example, and you can keep going, that's how you expand a radical of 2 terms, of the sum of 2 terms. So for example, if you were to take the square root of 1 plus x squared, which by the way, a lot of students who do not know algebra would actually expand that and think that it's 1 plus x because they would distribute the radical across the sum, which we know is very illegal We don't do that around here anymore because you know Jhevon will kill us. According to this, it's just like me plugging x squared for x in the above formula. It actually expands into 1 plus x squared over 2 minus x to the 4th over 8 plus 5x cubed x6 over 16 minus dot, dot, dot. So if you were to approximate this with a sum of two terms, the better approximation is 1 plus x squared over 2. And if you actually look at the graphs of these, you'll notice that when you are close to 0, those graphs actually behave in a very similar fashion, believe it or not. A good approximation with two terms, if you're very close to 0, to the radical of 1 plus x squared would be 1 plus x squared over 2. Now, unfortunately, many students, and in my experience, this is why I had to put it in my syllabus, because it was becoming crazy how many students thought this. They would see the radical of 1 plus x squared, and they would think that it's 1 plus x. Now, first of all, you have to appreciate that they're infinitely wrong, because expanding the radical of 1 plus x squared requires an infinite number of terms. So they're missing a lot, is the first thing. And the second thing is, even if they were to tell you, well, Jhevon, I'm just trying to say it's almost this number, they would still be wrong, because to use two terms, it would be much better to think of it as 1 plus x squared over 2 as opposed to 1 over x. So this is so wrong, it's not even funny. So don't do that. We know not to do that. Yeah, we'll stop there for now. What you can do is, in the meantime, so that you're not bored, try to look ahead. I'll post the notes here. And do the remaining problems. In particular, the example, what example? In particular, this example with the arctangent involved would be a good example to do, because that is something that I would actually test you on. This thing that I just spoke about with Euler's equation and the binomial theorem, somewhat optional stuff. I'm never actually going to test you on this, at least not in a non-bonus context. And but it's some things that you should know, you should be aware of. And I just, binomial theorem, definitely something you should know. Applying Taylor series to it allows us to extend the binomial theorem and expand things like radicals, which normally requires an infinite number of terms. Whereas if you're expanding integers, you'll always require only a finite number of terms if your power is a positive integer. Once your power is not a positive integer, you get an infinite number of terms. What happens when your n is a positive integer is eventually your Taylor series, all the coefficients become 0 after some point. And so you don't get anything. But yeah, that's another nice application of Taylor series. We'll talk a little bit more about applications of Taylor series next time. That is in the class that is for Friday this week. I'll finish this up, and then we'll move on to parametric equations. And I believe we're over time. I didn't even pay attention to when I actually started, but I'm pretty sure it's been about an hour now. So yeah, that's that. Welcome to the new reality. This is the new normal. This is probably how we'll be doing it for the remainder of the semester. Watch the lecture slowly. And the main thing you want to take away from this lecture is the fact that we can think of Taylor series as functions whenever the Taylor series converges to the functions, which is true for the series that I asked you to memorize in the last lecture. And we can literally swap out the Taylor series for the functions whenever convenient. You definitely want to know how to do this example because that is something I will definitely test you on. In terms of Euler's equations, very cool, very beautiful. Check out that video if you're interested. I won't probably directly test you on this, but in the future, it is going to be something that you'll realize that your professors kind of expect you to know out of nowhere, even though most people don't talk about it before the time they expect you to know it. And the binomial theorem, knowing about it is definitely something you should have known since high school algebra. However, expanding it with a Taylor series is something that you might need in the future as well. And it's just something that if it ever comes to a point where your professor decides to actually use this technique, they're going to kind of expect everyone to know what they're doing. So yeah, we'll stop there for now. Have any questions, you can drop them down in the description. I will post notes in the drop them down in the comment section. I will post notes in the description, PDF version of this OneNote book, this OneNote notebook. And yeah, you'll see a bunch more. Next, I'm going to do this example using series, and you guys can try this on your own. But this is probably the most important example for the remainder of this section. And with that, after those two examples, we can end this section. And that would kind of end our discussion for series in general. So by the next class, we should be done with series. Okay, we're out of time and I'm rambling on. It's probably because it's close to bedtime. I will see you guys in the next one. Be safe, take care. Hashtag stay at home, hashtag flatten the curve, hashtag Jhevon is going digital. Yeah, and that's it. Hopefully everything was clear, at least everything important. And I will see you guys next time in a couple days. All right, take care.